We're going to be talking about graphs of logarithms today. We're also going to be talking about properties of logarithms. So let's just look at the graphs first. And initially when we're looking at graphs, I'm going to compare them to exponential graphs. Because remember last class, we did talk about the graphs of exponentials, and we also know that logs are inverses of exponentials. If you have inverse functions, they are reflections about the line y equals x, and we also know that inverses switch x and y. Now b is not based on x or y, so the same restriction we had on b for exponentials, b has to be positive but not equal to 1, that applies to logs as well. This base has to be a positive base and can't equal 1. But we had this table that we started with exponentials. X was negative 1, 0, 1. Then y would be 1 over b, 1b, and a horizontal asymptote at y equals 0. If you switch x and y, you get the basic table that we're going to start with for logs. So now y is negative 1, 0, 1, and x is 1 over b, 1, and b. And even the asymptotes change, because x and y is switched. So instead of y equals 0, we have an asymptote at x equals 0, which means now it's a vertical asymptote. Also, our domain is switched, domain and range. For an exponential function, the domain was x exists in the set of real numbers and y is greater than 0. Well, now it's x is greater than 0 and y exists in the set of real numbers. So let's take a look at just exponential growth and decay and logarithmic growth and decay. So let me go ahead and put the function here. So remember, this is y equals b to the x, also down here. But if the base is greater than 1, it was growth. If the base was between 0 and 1, it was decay. Well, now we have the same kind of thing happening for logs. So this is y equals log base b of x, but this is also y equals log base b of x. And if the base is greater than 1, we can see the curve increases, so it's growth. But if the base is between 0 and 1, the curve decreases, so it's decay. Now let's look a little bit more at this because it is a little bit weird, if you've never seen a log graph before. First of all, the domain and range you can see here now. Here's my vertical asymptote at x equals 0. And so the curve is only to the right of it, so it's only x is greater than 0. But this curve will go forever down and forever up, so y is in the set of real numbers. And the same kind of thing happens with logarithmic decay. But we have these 3 points now. So let me see if I can get the table here. So here's our table. If the base is greater than 1, then b is greater than 1. So on the x-axis, here's 1 on the x-axis, so b will be somewhere to the right of it. So the point b1 will be somewhere here. Now if b is greater than 1, then 1 over b will be somewhere to the left of x equals 1. And so we have the point 1 over b negative 1 is down here. If b is less than 1, then b is going to be to the left of x equals 1. So now the point b1 goes up here. And if b is less than 1, then when we take the reciprocal of it, we're going to get something greater than 1. So on the x-axis, it winds up to the right of x equals 1. And we have the point down here, and that's what makes our decay graph. And then just comparing transformations, really it's about the asymptote that I'm trying to bring up here. So, if we have our transformations on it, we always know for exponentials that the horizontal asymptote is at y equals k. For logarithmic functions, your vertical asymptote is always going to be at x equals h. And I need to change this to a k. That was silly of me. So, horizontal asymptote, y equals k, vertical asymptote, x equals h. So now let's just get into some graphs. Let's take a look at them. So, let's say I wanted you to graph this one. We're going to do the same process we did for our exponentials. So strip off all the transformations, just take the base. So here is our parent function. And again, using that table that I have up there, 1 over b, 1 and b, negative 1, 0, and 1, vertical asymptote is x equals 0. So there's our table to start with. Now the first thing we're going to do is this negative. So that negative, since it's on the function itself, it's going to reflect about the x-axis, but it has the result of multiplying all the y-coordinates by negative 1. So the x's stayed the same, even the asymptote, because that's x. But these y's multiplied by negative 1, and I get that. Then we can apply the shifts. So we're going to go to the right 1 unit and up 3. So 1 unit right, 3 up. So we're going to add 1 to x and add 3 to the y. So all of these x values, including the asymptote, I added 1. And all of these y values, I added 3. And then I just plotted everything. So vertical asymptote, x equals 1, right there. And the point 1.5, 4. So 1.5, 4 is right there. The point 2, 3 is right there. And then the point 3, 2 is right there. And there is our graph, right there. And if we think of the domain and range, so the domain and range, well, we can see that the graph is only to the right of that vertical asymptote, so x has to be greater than 1. And y, for logarithms, it's always going to be in the set of real numbers. So now you guys try this one, and we'll, oops, I already have it. Try this one, and then we'll take a look at it together. So go ahead and pause the video right now and give it a shot. All right, so let's take a look. So this is what you should have. It gets a little tricky with e. So remember, natural log has a base of e. So I just, go ahead and work with it all throughout. At the end, I find approximations to help me graph, so I'll explain that. Here's our parent function. We are multiplying by negative 5 on x. That's what the formula or the equation says. So remember, x is always backwards, so you're really going to divide x by negative 5. So that will change the sign on x, so it reflects about the y-axis. And since we're dividing x by 5, it's a shrink by a factor of, really it would be better if I said a factor of 1/5. We multiply by 1/5. So I just divided all the x coordinates by negative 5. All of these divided by negative 5, including 0. But 0 divided by negative 5 is still 0. But the y's didn't change. Then this plus 3 does shift up 3 units, so we're going to add 3 to all the y's. So I just added 3 to all of those. But the x's didn't change. Now, when you're graphing with e, remember, you're not going to be able to graph very precisely, so we're just going to do very rough estimates. I wanted to find out what 5 times e was to get an idea, so I did that over here. Remember, you can think of e as about 2.7. So if I multiplied by 5, I got that. I mean, it's somewhere between 13 and 14. Really, I am not going to be able to do 1 over 13 versus 1 over 14. There's no way I'm going to graph that very accurately anyway, so I just estimated it to be negative 1/13. And then because e is about 2.7, when you divide by 5, 2.7 is kind of half of 5, so I just estimated it to be about 1/2. Again, we're doing these graphs by hand. That's going to be good enough. So that's what I did. I graphed these points. It was very, very narrow. It was definitely tricky, but my vertical asymptote's at x equals 0, and so about negative 1/13 too. So I did stretch out my x scale a little bit. So I put negative 1/13 is about right there, and then 2 on the y-axis. Negative 1/5 is going to go over a little bit more, up to 3. And then negative 1/2, 4 is right there. And I can see my curve. And there you go. There's your graph for that one. So that's graphing logs. It's not any different really than graphing your exponentials. So now we're going to move on to properties. Okay, so we actually have 4 properties that I'm going to prove. I'm not going to spend too long on the proofs. I'll go through them kind of quick, but if you're really curious, you can pause the video and try to really figure out what's going on. But the main thing we're going to focus on is using them. So let's take a look at just the proofs, like I said, really quickly. Okay, so there's something called the power property, and this last line does say the power property. When you're taking the log, oh sorry, this is supposed to be product. Hang on, let me fix that. I'm not going to test you on the names, so that's the good news. But yeah, that should be product. Okay, so the product property says if you have a product inside a log, then you can expand it into 2 separate logs using addition. And let's see why. So if you start with letting a equal log base c of m and b equal log base c of n, then if you just rewrite using logs or using exponents, you know the definition, around the world c to the power of a is m, c to the power of b is n. Now if I multiply these together, c to the a times c to the b, the properties of exponents tell us we can add these exponents together. But remember, we know that c to the a is m and c to the b is n. So now I have this. If I take this expression and rewrite it in logs, we have log base c of mn is a plus b right there. But we defined what a and b are up there, and that gets us our product property. So that was that one. Let's take a look at the quotient property. Quotient property works just like the product property. Again, here it is down at the bottom. So this time if you have a quotient inside a log, you can expand it to 2 separate logs using subtraction. And the proof works exactly the same. So we start with a equaling this log, b equaling this log, then we rewrite them in exponential form. But this time instead of multiplying together, we're going to divide them, and our properties of exponents say we can subtract the exponents. But we know c to the a is m and c to the b is n, so I just replace them right there. Rewriting it in log form, log base c of mn is a minus b, right there. But in the very beginning we said what a and b were, and so if we replace it, we wind up with a quotient property. All right, let's look at a third property, which is called the power property. All right, so here's the power property, and it's similar, but it won't be exactly analogous because it doesn't have the same analogy that that product and quotient rules have. But if we still start off with a log, but we're only going to start off with 1 this time. Rewrite it as an exponential. C to the a is m. Now let's raise both sides to a power, because this is the power property. The properties of exponents say when you have a power raised to another power, you can just multiply the exponents. Now I'm going to rewrite in logs, but I have 2 bases here, so we're going to use base c. So starting at this base and going around the equal sign, we have log base c of m to the b equals ab. Log base c of m to the b equals ab. But I just reversed the order here, and we know from the very beginning what a was, and so there it is. This is the power property. The power property simply says if you have an exponent in the argument of a log, that exponent has to be on the entire argument, then you can move that exponent out in front of the log and multiply by the exponent. And that's power property. All right, let's take a look at our fourth and last one, change of base. Okay, so here's the change of base formula. Now, I'm going to start at the bottom here. So the change of base formula says this. If we have one base, we can actually change this base to any other base we want. And we just rewrite it this way. So you take the argument and put it in the numerator, and you take the base and put it as the argument in the denominator using this new base. And we typically use change of base formula because a lot of calculators don't do base 10 or base E. Or sorry, I shouldn't say that. A lot of calculators only do base 10 and base E. So how do you use a calculator to find other logs? You end up having to use change of base formula. So let's see where this comes from. Again, I'm just going to start by defining this log here. And if I rewrite it using exponents, I have a to the power of u is equal to x. Now I'm going to take the log of both sides. And I'm just going to use a generic base. This is no base in particular, so I put log base c in front of this and a log base c in front of the right-hand side, and I wind up with this. But remember, we just learned about the power property. The power property says if I have a power in an argument, I can take that power and move it in front, which I did. So now this is u times this log. Because it's multiplication, I can divide both sides by that log. I wind up with this. But u was defined as log base a of x, and voila, we have the change of base formula. So those were our properties. Like I said, I'm not going to test on the proofs. I think it's good you see where they're from, but now we're going to focus on using them. Before we do that, though, let's just summarize this again. Okay, so here's everything that we just said put together. This is the important thing that you need to know. Ideally, I know our tests are open notes, but these are things you should memorize because you're going to use them often enough in later math classes. Honestly, you're probably going to use these enough that you're just going to naturally have them memorized, but it is a good thing to have these memorized. So again, the product property. If you have a product inside the argument of a log, you can expand it using addition and into two separate logs. If you have a quotient in the argument of a log, you can expand it into two separate logs using subtraction. And that makes sense. I mean, remember, logs are exponents, and so when you multiply with the same base, you add the exponents. When you divide with the same base, you subtract the exponents. And then here we have a power on the argument of a log. So whenever you have a power on the argument, that you can pull the power out in front and multiply the log by that power. And then we have the change of base formula that says if you have a log in one base, you can change that to any base you want. We typically change it to base 10 or base E. But you can change it to any base you want. You put the original argument as the argument in the numerator, and you put the base as the argument in the denominator. And voila, there's your properties. So let's practice using these. So let's expand this guy. So we're going to do this together. It's not that bad. It really isn't. So you have to look at your argument. Now we have a lot of things going on in the argument, actually, because I see a power, I see a product, I see a quotient. The quotient is the first thing, because that's really what's cutting this into two things. So we're first going to expand it using the quotient property. So I'm going to do the numerator minus the denominator. So that's our first step. Now, on this side, I do see a product and a power. Now remember, I can't use the power property yet. The power has to be on the entire argument. And right now the power is only on the y. So I have to use the product property first, and then I'll be able to use the power property. So this one term is first going to split up like this. I have a product of x and y squared, so I can use addition and x and then the y squared. And then, now that the 2 is on the entire argument, I can move that 2 out in front and write it like that. Now let's look at this term. Remember, radicals are exponents, and that's going to be important with our logs. We can think of that as z to the power of 1/2, and now that is a power that we can pull out, and then there's our final answer right there. We know we're done because we can't split up these arguments anymore. And thinking about our properties, I can just barely fit it. We have product, quotient, and power. I don't see a power, quotient, or power here. I don't see a product, quotient, or power in this argument, and I don't see a product, quotient, or power in this argument. So I know I'm done. So that's what we mean by expanding. So I have one down here. I want you guys to give this one a shot and see what you get. So definitely pause the video right now and try it out. All right, so now let's take a look at this one. So again, there's a whole bunch of stuff going on here. Just take it one step at a time. We do have the quotient that's first dividing this into two pieces. So I first use the quotient property, expand it to two separate logs using subtraction. And here's a numerator, and here's a denominator. Now remember our roots, our roots are exponents, so a fourth root is like a 1/4. And then I went ahead and just took care of this power. The 5 is on the entire argument, so I moved that out in front. And then we have the same thing here. Now the 1/4 is on the entire argument, so I moved the 1/4 out in front. And now the next thing that's dividing this into two parts is the product. Again, this 3, remember that's a power, but it's not on the entire argument, so I can't do anything with the 3 yet, but I'm going to split it up first using the product property. And now I can move that 3 out in front. Over here on this one, this addition sign is causing some problems. I do have a power. It's not on the entire argument, and there's no way to split this up because I don't have a addition rule for logs. So this argument actually will never get split up. Notice in my final answer, it's still there. So I just moved the 3 out in front. That was it. But now I can distribute the 1/4 to each term. I should actually distribute the 1/4 each term. There we go. So the 1/4 gets multiplied by that, and there's our answer. I will go ahead and box it. Now, we won't use this so much. Like, you're going to have to do it, but you won't see a purpose for doing this so much in this class. But there are things in calculus that actually become a lot easier if we can expand it. I mean, take a look at this original expression here. This thing looked really messy, this natural log of all of that. But now I'm just doing the natural log of x, or the natural log of x squared plus 6, or the natural log of y. We've made it so much simpler. So when we do the calculus of these expressions, it's actually much easier when we expand them. That's going to be a key use of this. So you won't see it this year, but just trust me, it's going to come in handy next year. All right, let's look at something else called condensing. So condensing is just going backwards. What if we have it expanded out and we wanted to put it together? So we're just going to do all those rules backwards. So in general, if you ever see a coefficient in front of the log, you're going to use the power property. So we're going to do that first. We're going to put the 3 as an exponent. We're going to put the 1/4 as an exponent. We're going to put the 2 as an exponent. And there's no exponent here. Now, just a little note. It's totally up to you. There's no rule that says when you move this back that you have to either write it as a 4th root, you have to write it in radical form, or you have to write it in exponential form. So you write however you want to write it. I'm going to leave it in exponential form. All right, so now let's take a look. If we were to do this, I'm just going to do this kind of a longer way, but then I'll show you a shortcut you can take. Because now it's just a matter of, we've used our power property, so now it's just subtractions and additions. So it's going to be using product and quotient. If I just do them 2 at a time. So this is quotient, because there's subtraction. So I'm going to do log of x cubed over 3 to the 1/4. But then I still have plus log z squared minus log y. Okay, now I'm going to go ahead and combine those two together. It's an addition sign, so that means I'm going to multiply the arguments. So I will have x cubed z squared over 3 to the 1/4, but then it's minus log y. All right, now I'm going to divide. So it's going to be log of x cubed z squared over 3 to the 1/4 divided by y. But we know division, you multiply by the reciprocal, so it's going to be x cubed z squared 3 to the 1/4 times 1 over y. So my final answer will look like this. And voila, there's my answer. Now, like I said, this is a longer way to do it, but this is very, straightforward. We can do a little shortcut. So first of all, if you didn't follow what I did, I would encourage you to pause the video and just, again, pay attention to, first there was subtraction. So I used the quotient property to combine. Then there was addition. So I used the product property to combine. Then there was subtraction again. I used the quotient property to combine. But when I'm dividing with fractions, I can multiply by the reciprocal and get here. Now you still have to do this. Here's the shortcut. You still have to do the power property. So this 3 still has to become the exponent. This 1/4 still has to become the exponent. This 2 still has to become the exponent. But once you got here, just take a look. Anything that's positive is going to go in the numerator. Anything that's negative is going to go in the denominator. We had a positive log x cubed and a positive log z squared. X cubed z squared went in the numerator. We had a negative log 3 to the 1/4 and a negative log y. 3 to the 1/4 and y went in the denominator. So you can go right from here down to here, and you don't have to do all of this. But, if you draw a blank, you can always do it the long way. Okay, so there's that problem. Now here's one for you to try. You guys give this one a go. All right. Now, you're going to wind up with the same thing. I'm just going to say this, but then I'll just work it out real quick. If you take a look, do we combine this first or do we distribute? How do we know which one to do? And the answer is yes. You can do it either way. It doesn't matter. You can either condense first, then multiply by the 1/2, or you can distribute the 1/2 first and then condense. So, all right. So I'm going to go ahead and just distribute it out. So we have this, and I'll work this out quickly. Because there really aren't, don't make these harder than they are. They're really not that bad. All right, so now that I've got that, I've distributed my 1/2 to the terms that it goes to. I'm going to move everything that's an exponent, or everything that should get an exponent. I'm going to move it. Log base 3 of n to the 5/2 minus log base 3 of z plus log of x to the 7th. Okay, so I have all of that. So now, whoops. Oh, I should have had I didn't mean to trick you like this. There should be a base 3 right there. Let's give a base 3. That does bring up a good point, though. If you do not have the same bases, you cannot condense. And there's no shortcut. There's nothing you can do. You just leave it separated. All right, so now that we have that, I'm going to do what I was saying before. I'm ready to go to my final answer. So I'll put a big old fraction bar here. If it's a positive log, the argument goes in the numerator. And if it's a negative log, the argument goes in the denominator. Positive, positive, and positive. So m to the 1/2, n to the 5/2, x to the 7th, all in the numerator. This was a negative log that goes in the denominator. Oops. And we're done. Yay! So it really is that easy. All right. So we're almost done here. Let's look at a couple more properties. These are just handy ones to know. All right, so I purposely have not actually written these out, but let's take a look. What I would do actually is encourage you, pause the video right now and just see, can you figure out what these are? And then we'll compare. All right, so hopefully you pause the video. Let's just look at this. Remember, whatever the answer is, b to what power is 1? Oh, it's b to the 0. It doesn't matter what your base is, as long as your argument is 1. I mean, your base obviously has to be positive and not equal to 1. But as long as your argument is 1, the answer is 0, always. Similarly here, b to what power is b? It's 1. What about here? B to what power is b to the x? It's x. And this one's a little harder to see, but trust me, it's just going to be x. Remember that when you have, since exponents and logs are inverses of each other, if the bases match, they cancel out, and you're left with the x. Same thing here. We have an exponent and a log in the same problem. The bases match, so they cancel out, and you're left with the x. So handy ones to know. So using those, let's see if we can simplify these without a calculator. I'll work these out, but if you feel pretty confident, I would actually, again, encourage you to pause the video right now and try these on your own. All right, there's different ways to do these, but I want to just look at how you can specifically use the properties that we looked at above. So if you can get the bases to match, think about these things right here. So if you can get the bases to match, that's going to help out a lot. I see a base 4 on the log, and I know 16 is a base 4. So if I write this as the cube root of 4 squared, but then I know that the cube root could be written as an exponent, so I can make this 2/3. Well, now the bases match. It's just going to be 2/3. And voila, no calculator needed. Part B, let's see here, 354, that's not a power of 3. But I see another log here with the same base, with subtraction. I can first use the quotient property to write it. The argument is 54 over 2, which, that's 27. Oh, and I know 27 is 3 cubed. Oh my gosh, 3's all over the place. But the bases of 3 cancel out, and then we're just left with the 3. For part C, don't forget, if the base isn't written, it's an invisible 10. And now the bases match. Your answer is 7. And then part D is actually a lot like part A. 16 is 2 to the 4th, but we're taking the 5th root. So we can say the argument is 2 to the 4/5. Now the bases will cancel. We're just left with 4/5. Okay, so we just have one more thing, and that is change of base. So with this one, if you have a calculator, a scientific calculator, if you take a look at that, every scientific calculator is going to have a button that has a log on it. And it just says log, L-O-G. Now remember, we looked at before, if there's no base written, that's base 10. So if you have one of those buttons that just says log, that is specifically log base 10. Now you probably also have ln somewhere on that calculator. Sometimes it's in the shift, like you have to hit the shift button before a button to get it. But you probably have ln somewhere on there, and that's specifically base E. Now more and more calculators are getting the capability to do any base, like a base 2 or a base 4. But not every calculator has it. And so you still need to know the change of base formula. Also, there are some things that you do later on, like in calculus or whatever, where you still want to change it to another base. It's weird, but like in calculus, when you're doing the calculus of base E, even though e itself is kind of a messy number, 2.71828, whatever, it keeps on going. The calculus of e is so much better. So if you can still change back to base e, it's a lot nicer to work with. So that's the purpose for change of base. It's just to rewrite it so that you can use a calculator to evaluate. So according to our formula, we can change base 2 to any base, and I'm going to change it to base 10, and we put the original argument on top, we put the base on the bottom, and we also could have used the natural log. Now if you have a calculator that can do these, I would encourage you actually to try it out. Actually type in log of 7 over log of 2. See what that answer is. Type in natural log of 7 over natural log of 2. Now be careful, like for the graphing calculators, and this is true for a lot of calculators, as soon as you hit that log button, it forces a parenthesis to be open. So you have to make sure you close that parenthesis before you hit the division key. And then again, log base 2. So for a lot of calculators, not all of them, but for a lot of calculators, this is what it looks like when you type it in. And I'll just do it really quickly on my calculator. Log of 7 divided by log of 2. And if you did this correctly, you should get about 2.807. So go ahead, pause the video, try the next one, see what you get, but it's going to be done exactly the same way. So pause it if you want, but here we go. If you change it to base 10, it looks like this, log of 13 over log of 4. If you change it to base e, it's going to look like natural log of 13 over natural log of 4. But you're going to get the same exact answer no matter which one you do, and it should be about 1.850. Now one tiny quick note. Yes, I know that a lot more calculators these days are getting the functionality to do logs of any other base. However, you still, for me, need to know how to change it to base 10 or base e. I will be requiring it, so just keep that in mind. All right, so that's it. Have fun, and I will see you in class. Bye.